Hello and welcome back. We're talking about chemical reaction equilibria in the last class, and we discussed how we handle the enthalpy change due to the chemical reaction, what standard states are, and how to calculate enthalpy change for a reaction from heats of formation data. We also mentioned that just like enthalpy change due to reaction, other thermodynamic variables such as Gibbs free energy change upon reaction can also be calculated on similar lines. What we'll do today is to lay the theoretical background so that we can analyze chemical reaction equilibria through thermodynamics. Let's start with the quantity called as stoichiometric number. We already talked about it during enthalpy change upon reaction discussion. What it is essentially it is the number of moles of a particular species that are reacting in a balanced reaction or that are produced in a balanced reaction. So for example, if I have something like this, nu A time nu A moles of A plus nu B moles of B reacting to give nu C moles of C and nu D moles of D, then we call each of these quantities nu A, nu B, nu C, and nu D as the stoichiometric numbers, right? Notice that we have used an absolute sign here so that they're always positive in the way a balanced chemical reaction is written, but stoichiometric number actually is negative for the reactants. So in that sense, for A, the stoichiometric number is actually negative of nu A. For B, it is negative of the absolute value of B nu B. For C, it is positive. For D, it is positive. So these are the actual stoichiometric numbers for each of the four species that are present in that particular reaction. If I have something like a water gas shift reaction, for example, CO plus H2O giving CO2 plus H2. In this particular reaction, the stoichiometric number for carbon monoxide is -1 because it is a reactant, and the number of moles in this particular reaction for CO are 1. For H2O also it is -1. For carbon dioxide it is 1, and for hydrogen it is 1. So all the products get the positive sign, the reactants get the negative sign, and then with the appropriate number of moles that are present in this particular reaction. Similarly, if I have a direct conversion of CO2 to methanol, a reaction for direct conversion of CO2 to methanol, for example, CO2 plus 3H2 giving CH3OH plus H2O. In this particular reaction, the stoichiometric numbers for carbon dioxide is -1, for hydrogen is -3, for methanol it is 1, for water it is 1, right? So this is the quantity we call a stoichiometric number. This plays an important role. Now, in addition to this, notice that the number of moles at any instant in time during a reaction is going to depend on two things. One, the initial number of moles. Let's call that as Ni, and because it is initial, we'll call it as Ni naught. So it will depend on the initial number of moles for each of the chemical species, and also it will depend on the extent of the reaction, how far the reaction has proceeded, right? The number of moles of A that react will be related to the number of moles of B that will react according to the stoichiometric numbers. That would also be related to the number of moles of C and D produced according to these stoichiometric numbers, because the reaction has to proceed. So in that sense, the final composition of a mixture in a chemical reaction is going to depend, in addition to initial number of moles, it will actually depend only on one other variable, and we can call that as the extent of the reaction. In general, for good bookkeeping, what is done is a new variable is defined to enable us to do this, and we will call this variable as the reaction coordinate. And the way we define reaction coordinate is by defining the quantity dNi over nu I, right, where dNi is the change in number of moles, nu I is the stoichiometric number. It's positive for products, negative for reactants, etc. And this quantity, as it turns out, is going to be constant irrespective of what species we are considering. Right, if that species is present in the reaction, then this quantity is going to be constant. So for example, in the previous case, then dNi by nu I for A will be dNa by nu A being negative for the reactant, dNb by, it will also be equal to dNb by nu B, again nu B is negative. It will also be equal to dNb by nu C, because C is a product, nu C is positive, and dNd by nu D. Again, nu D is positive, right? So this ratio is constant, and we're going to call this ratio as d epsilon, and this epsilon is the quantity we are going to identify as reaction coordinate. So d epsilon is the differential change in the reaction coordinate. Now, I can actually write the final number of moles in terms of the initial number of moles and the reaction coordinate for each of the species using this expression. For example, as it turns out, since for any species I, dNi by nu I is d epsilon, what I can do is integrate this particular expression. If I integrate it from the initial condition of Ni naught, that's the initial number of moles, to the final number of moles, let's say is Ni, dNi is going to be nu I, that's a constant, integral of 0 to how far the reaction has proceeded. If the reaction coordinate is epsilon, that's when we get the final number of moles Ni, let's say, then it will be integral from 0 to epsilon d epsilon. And if I take this, it will be Ni minus Ni naught is going to be nu I times epsilon, or N is going to be Ni naught plus nu I times epsilon. This is Ni. So the final number of moles is going to, for each of the species, is going to be related to the initial number of moles Ni naught and the reaction coordinate epsilon. So the only thing I need to calculate the final number of moles present during a reaction is simply the reaction coordinate, of course, in addition to the initial number of moles we have taken for that particular reaction. So I don't need to identify the number of moles for each of the species or track them for each of the species along the reaction. I just need to track the reaction coordinate, and at any instant in time I can readily calculate the number of moles for each of the species. And that's again because each of them are related via the stoichiometric numbers for that particular reaction. Now, what this will help us is to calculate the number of moles, but in general in our thermodynamic analysis, as you can recall, what we are interested most of the times is the mole fraction. And in fact, we can do a little bit of manipulation for this reaction, we can do a little bit of manipulation for this particular equation to get the mole fraction also. Let's say the mole fraction is yi, and if Ni is the number of moles for each of the species, then the total number of moles, will drop the subscript, we'll call N to be the total number of moles, and it's simply going to be sum over all Ni's. And because Ni, we call it as Ni naught plus nu I times epsilon, right? This is summation over all the species I present, and this will be summation over I for all the species present Ni naught plus summation over I for all the species present nu I times epsilon. And because we are summing it over all the species I. Let's call this quantity as N naught, which is the total number of moles at initial condition. And notice that the second term is sigma nu I times epsilon. We can do a little bit of manipulation to this term. Sigma nu I times epsilon is going to be epsilon times sigma nu I. Epsilon is constant irrespective of the species, so it can come out of the summation. And we have sigma nu I. Instead of writing sigma nu I each time, we can write it as simply nu being summation over all nus for each of the species. So this equation then reduces to N naught plus nu times epsilon. This is the total number of moles at any time t, and total number of moles at the initial time is N naught. Now once I have N, and I also had Ni from the previous expression, then Yi is simply going to be Ni over N, and that would be Ni naught plus nu I times epsilon over N naught plus nu times epsilon. So the numerator is the change for the species I plus the initial number of moles for I, and the denominator is the change, overall change for the reaction, the number of moles, overall change in the number of moles for the reaction, plus the initial total number of moles N naught. So that would be essentially Yi, and of course it makes sense, right? So if there is a single reaction present, then the mole fraction is simply given by this particular expression. And we know what each of these terms are, right? Ni naught is the initial number of moles for I. N naught is the initial total number of moles. Nu I is the stoichiometric number for I. Nu is the total stoichiometric number, which is sigma nu I, and epsilon is the reaction coordinate. So once I know epsilon, I can calculate mole fraction at any point in time during the course of a particular reaction. This is for single reaction. What we'll do is quickly work on one example to illustrate the concept of calculating the mole fraction or the expressions for mole fraction in terms of the reaction coordinate before we move on to look at how we handle multi-reaction scenario. Right. So let's take an example. Let's say I have the same example, a water gas shift reaction. So the reaction reads CO plus H2O giving CO2 plus H2. That's the water gas shift reaction. The initial number of moles Ni are given here. Let's write this. Ni naught for CO, for H2O, for CO2, for H2, and it turns out in this particular reaction there is also an inert nitrogen present, so we'll write the initial number of moles for nitrogen also. So the initial number of moles for CO are 4, for water it's 2, for CO2 it is 2, hydrogen is 1, so some of the products are still present at the initial time, and there is an inert present, 4 moles of inert present. Right. These are the initial number of moles for each of the species. Remember, all the reaction is occurring only for these 4 species. We also need to include the inert because essentially inert will influence the mole fraction. So we'll still write the number of moles for inert as well. Right. Now, what we want to know is find expression for Yi. And because now we have 5 species, although only 4 are in the reaction, there are a total of 5 species. So we want to find the expression for the mole fraction for all the 5 species in terms of the reaction coordinate epsilon. That's what we want to do. Okay. So to do that, we'll use what we just discussed. The first thing we want to find is the total number of moles at the initial condition N naught, which is sigma Ni naught, and that turns out to be 4 plus 2 plus 2 plus 1 plus 4. That's 6, 8, 9, 13. Those are the total number of moles at the initial condition. Now, we also want to find the overall stoichiometric number, which is nu, which is defined as sigma of nu I, right? What I'll do is, just for sake of easiness, I'm going to write nu I. This thing in yellow is something I'm writing. It's not given in the problem statement. I'm writing it for our understanding. Nu I for CO is -1, obviously, because it is a reactant. For water, it is -1 again, because it's a reactant, and 1 mole is going into this balanced reaction shown here. For CO2, it is 1. For hydrogen, it is 1. And for nitrogen, it's an inert. It's not participating in the reaction. So the stoichiometric number is going to be 0 for nitrogen. Now, with these values of nu I, if I sum sigma nu I, what I get is -1, -1, +1, +1, and a 0. That would add up to 0. So for this particular reaction, including the inert present, the overall stoichiometric number nu is going to be 0. Now, once we have that sorted out, it's pretty straightforward to write the expressions for Yi. Recall, the expression for Yi is Ni naught plus nu I times epsilon over N naught plus nu times epsilon. That's the expression we had earlier. So we're going to use that expression to write Yi for each of the species. For CO, it's going to be Ni naught. Ni naught for CO is 4. The stoichiometric number nu I is -1 times epsilon, so that's 4 minus epsilon over N naught. So since we have this, what I'll do is the denominator is common for each of the species. So I'm going to write N naught plus nu times epsilon is going to be 13 plus 0 times epsilon is 0. So the denominator is going to be 13 for each of these, and it's constant. So that's going to be the value for N naught plus nu times epsilon. Now, that's for the first species. So the mole fraction of CO is 4 minus epsilon over 13. So if I know epsilon, I can calculate the mole fraction for CO. Similarly, for water, it's going to be Ni naught for water is 2 minus nu I for water is -1 times epsilon over 13. So it's 2 minus epsilon over 13. Similarly, for CO2, Ni naught for CO2, as you can see from the table, is 2. Nu I for CO2 is 1, so it is 2 plus 1 times epsilon is 2 plus epsilon over 13. And finally, for hydrogen, H2 is going to be initial number of moles for hydrogen, which is 1, right, plus nu I again for hydrogen is 1, so it is 1 plus epsilon over 13. So these are for the species that are present in the reaction. In fact, we have one more species, which is an inert, that is nitrogen. Y for N2 is going to be Ni naught for N2, which is 4, plus nu I for nitrogen is 0, so 4 plus 0 is 0 over 13, right? So these are the number of moles in my particular reaction, or sorry, these are the mole fractions for each of the species in my particular reaction at any point in time. And the only thing that you need to know to calculate them is the reaction coordinate, right? In fact, one other thing I usually do when I solve problems such as these is make sure that all the mole fractions add up to unity, right? Make sure that sigma Yi is going to be 1. And if you actually go through the math, you will see that the denominator is same. The numerators all add up to 13, so that sigma nu I, Yi is going to be 1. That's how I cross-verify whatever expressions I usually write for these type of problems, right? So that's how we handle a single reaction scenario. For the sake of practice, let's do one more problem, right? This had a overall stoichiometric number equal to 0. So the denominator does not involve the reaction coordinate, but in certain cases it can. Let's see an example. This time the reaction we are looking at is for formation of ammonia, everything in the gaseous phase again, half N2 plus 3 by 2 H2. So the moles don't have to be necessarily integers, they can be fractions as well, as in this scenario, will give me 1 mole of ammonia. This is the reaction I'm looking at. And as earlier, let's write the initial number of moles and nu I. Well, the initial number of moles are given, right, for N2, for H2, and for ammonia. The initial number of moles are 4, 15, and 1. And what we want to find is expression for yi in terms of the reaction coordinate epsilon. So unlike the previous case, now there is no inert, but what we want is expression for yi, which, as we recall, is ni naught plus nu I times epsilon over n naught plus nu times epsilon, right? So which means I need to know the reaction, the stoichiometric numbers as well. So as earlier, let's write the stoichiometric numbers. For nitrogen, it is -half, it's a reactant. Similarly for hydrogen, it is -3/2, and for ammonia, it is 1. Once I have the stoichiometric number, what I can do is go back and calculate the denominator first. N naught is sigma Ni naught. It is 4 plus 15 plus 1, which is going to be 20. And similarly, nu is going to be sigma of nu I, which is -half, -3/2 plus 1. So that's -2 plus 1, which is -1. And because n naught and nu are known, now I can write the denominator n naught plus nu times epsilon. The denominator is going to be 20 minus 1 times epsilon is epsilon. So now in the denominator I have the reaction coordinate term also, unlike in the previous case. And I have that because the overall stoichiometric number is not 0. In the previous case it was 0. But anyway, the denominator now is 20 minus epsilon. Now if I want to write the expressions for the mole fractions, yn2 is going to be ni naught for n2, which is 4, plus nu I for n2, which is -half, times epsilon over 20 minus epsilon. Similarly for hydrogen, it is 15 minus 3 by 2 times epsilon by 20 minus epsilon. And for ammonia, it is 1, this time it's a product, so nu I is positive, 1 plus epsilon by 20 minus epsilon, right? So those are the expressions for each of the mole fractions. And as in the earlier case, we can cross check, and it turns out that if you add all these mole fractions, it will be 1, which it should be, right? So that's how we cross checked what we just derived. So those are a few examples on how we express the mole fractions in terms of the reaction coordinates when we have a single reaction. Now let's consider the case of a multiple reactions. And in case of multiple reactions, what we'll do is we'll identify the stoichiometric number as nu ij. So this is the stoichiometric number for species I in reaction J. Earlier we only had one reaction, now we have more than one reaction. So in each of these reactions, the stoichiometric number for the species I might be different. So we'll identify as nu ij. And similarly, we also have a reaction coordinate. This reaction coordinate for each of the reactions might be different. So we'll denote it by a subscript j. So epsilon j stands for the reaction coordinate for reaction J, right? This being the case, the species, the change in number of moles of species I, D and I, is simply going to be, as earlier, it's going to be Ni naught, the initial number of moles, plus the change due to each of the reactions. So what I need to do is sum it over all the reactions J, nu Ij, epsilon j. If there is only one reaction, then it will be simply nu I times epsilon. If there are more than one reactions, then we have to account for changes in each of these. So it's going to be nu Ij times epsilon j, right? And to calculate the mole fraction, we can derive this expression, but we'll just write it down. It would be simply Ni naught plus sigma over j nu Ij epsilon j over N naught plus sigma over j nu j epsilon j, right? And here nu j is again defined as the overall stoichiometric number for reaction j, which is summation of nu ij's for all the species in the reaction j, right? That's how we define it, and this will be the expression for mole fraction of species I when there is more than one reaction occurring, right? Again, we can demonstrate this calculation using an example. So let's take one quick example. We'll consider the case of direct conversion of carbon dioxide to methanol. CO2 plus 3H2 gives methanol, CH3OH plus water. All of them are in the gaseous phase at high temperature and pressure. And a side reaction occurs as well. CO2 plus H2 is going to give CO plus H2O. This is what we call as the reverse water gas shift reaction, right? Both these reactions occur simultaneously. And let's again write what is given. CO2, H2, CH3OH, H2O, CO, and then an inert N2 is also present in the reaction. The initial number of moles for each of these species, Ni, is 4, 10 moles of hydrogen, 0 moles of methanol, 1 mole of water, 1 mole of CO, and 5 moles of N2. So this is what is present, and what we want to calculate is Yi in terms of epsilon 1 and epsilon 2. So this we are identifying this as reaction 1 and this as reaction 2. So epsilon 1 is for reaction 1, epsilon 2 is the reaction coordinate for reaction 2, and we want to find expressions for Yi, each of the species I, in terms of this epsilon 1 and epsilon 2. Now to be able to do this, what we'll do is we will write the stoichiometric numbers for each of the species I in the reaction, right? So what I'll do is nu I in reaction 1 and nu I in reaction 2, right? In reaction 1, we'll use the same table. In reaction 1, CO2, it is -1. For hydrogen, it is -3. For methanol, it is +1. For water, it is +1. There is no CO, there is no N2, right? And summation of nu I1 is what we called as nu1, the overall reaction coordinate, the overall stoichiometric number for reaction 1, and this turns out to be -1, -3 is -4, plus 2 is -2. Now for the second reaction, CO2 is again -1, hydrogen is also -1, there is no methanol in this particular reaction, water is again +1, CO is +1, and there is no nitrogen. And so nu I2, or summation of nu I2, is going to be what we call as the overall stoichiometric number for reaction 2, which turns out to be 0 in this case, -1. -1 plus 1 plus 1 is 0. So once I identify this, the next thing I want to do is calculate N naught, right? Calculate N naught, and from the given information it is sigma of Ni naught, and from the given information this value is 4 plus 10 plus 0 plus 1 plus 1 plus 5, which turns out to be 14, 15, 16, and 20, 21, right? And the denominator term, let's write that expression for yi one more time here. Yi, as we know, is Ni naught plus sigma over j nu ij epsilon j for reaction j over N naught plus sigma over j nu j epsilon j. That's the expression, right? Now, let's first write the denominator because it is common for each of the species. Like in the single reaction case, let's write that down. N naught plus sigma of nu j epsilon j running over all j. So it will be for both reactions 1 and 2. So we can expand it. It will be nu 1 epsilon 1 plus nu 2 epsilon 2, and that would be 21. Nu 1 is -2 times epsilon 1 plus 0 times epsilon 2. So that's going to be 21 minus 2 epsilon 1 in this particular case. That's going to be the common denominator for each of the species. Now I can write the expression for mole fraction. Y for CO2 is going to be initial number of moles for CO2, which is 4, minus nu for CO2 in the first reaction, which is -1 times epsilon 1, plus nu times nu for CO2 in the second reaction, which is again -1 times epsilon 2 over the denominator, which is 21 minus 2 epsilon 1. Similarly for hydrogen, it's going to be 10, the initial number of moles, minus nu for hydrogen in the first reaction is 3 times epsilon 1, in the second reaction is 1 times or -1 times epsilon 2 over the common denominator, which is 21 minus 2 epsilon 1. For methanol, there is no initial moles for methanol, and it is produced only in the first reactions, and nu for methanol in that reaction is 1 times epsilon 1, nothing in the second reaction, over 21 minus 2 epsilon 1. Y for CO is going to be the initial number of moles, which is 1, nothing in the first reaction for CO. It's nu for CO in the second reaction is 1 times epsilon 2 over 21 minus 2 epsilon 1. And finally for N2, the initial number of moles is 5, the stoichiometric number in both the reactions is 0, so the numerator is going to be simply 5 over the denominator is 21 minus 2 epsilon 1. So those are the 5 expressions I'm looking at for the mole fractions in terms of epsilon 1 and epsilon 2. And notice that because there are 2 reactions, now I need 2 reaction coordinates to calculate each of the mole fractions. And again, as earlier, if you add all these mole fractions, the summation should go to 1, and in this case as well it does, right? So that's how we handle the scenario for a multi-reaction equilibria. We can express each of the mole fractions in terms of the reaction coordinates of as many reactions as are present. Now, once we identified that all I need to define the mole fractions is simply the reaction coordinate for each of the reactions that is occurring, the next logical thing to do is analyze the thermodynamic equilibrium when there is a reaction, right? We'll do that when we come back in the next class. Thank you.